Welcome to lecture number 2 of Thermal Engineering Module 5. In this module, we will be discussing combustion in IC engines. First, we will discuss the combustion in SI engine. In SI engine, homogeneous mixture of vaporized fuel, air, and residual gases is ignited by a single intense and high temperature spark between the spark plug electrodes. The temperature will be around 10,000 degrees Celsius and it will generate a pre-flame which spreads to envelope of mixture for combustion. And we can see from the figure that the combustion in SI engine can be classified into three stages. The first stage is ignition lag, and the second part is known as propagation of flame, and the third one is afterburning. The first stage is called the ignition lag or preparation phase. There is some time interval between the first spark given to the mixture and the first flame appears out of the mixture. This time interval is known as the ignition lag. Due to this combustion, at point B, there is a clear rise in cylinder pressure. This ignition lag represents the pre-flame reaction. The angle changed by the crank between the points A and B is known as the ignition delay angle. The first phase or the preparation phase in the stages of combustion in SI engines depending upon different factors such as the temperature of fuel, pressure, molecular structure of fuel, density and air-fuel ratio in the combustion chamber. The second stage is propagation of flame which is represented by BC. This is the most important stage of the combustion in SI engine. When the first flame appears after the spark at point B, this flame travels to the surrounding and burns the fuel in different layers. This fuel burning rate and flame speed are noticeably low at the beginning, and there is a small but steady pressure rise in the combustion chamber. It also releases heat energy in the combustion chamber, which is transferred from the burnt to the unburned charge. The speed of flame propagation is becoming very high in the range of 15 to 35 meter per second. The curve BC on this diagram represents the rate of pressure rise. The rate of heat transfer to the cylinder walls is very low at the beginning of this flame propagation phase. The last stage is afterburning and it is represented by CD. After point C, a continuous burning of the remaining fuels in the cylinder and a reassociation of the dissociated gas in the combustion chamber occurs. During the expansion stroke, the combustion of air and fuel mixture continues after point C. This phase is called afterburning, and during this stage, no pressure rise is happening. Now we can see effect of engine variables on ignition lag. When the self-ignition temperature of the fuel is high, the longer will be the ignition lag. It will take time to self-ignite the fuel. So the ignition lag will be more. Then mixture ratio, the mixture is richer than the stoichiometric ratio, then the ignition will be faster, so the ignition lag will be smaller. And initial temperature and pressure or the high compression ratio and the high chemical reaction rate, this will all increase the speed of ignition. That means it will reduce the ignition lag. And lower compression ratio and higher electrode gap is desirable for SI engines. And ignition lag increases linearly with engine speed when measured in degree crank angle. Spark advance is desirable in higher engine speed. Now flame propagation. Rate of flame propagation affects the combustion process in SI engines. Higher the combustion efficiency and fuel economy can be achieved by the higher flame propagation velocities. But unfortunately, the flame velocity of most of the fuel range between 10 to 30 meter per second only. Auto ignition. A mixture of fuel and air can react spontaneously and produce heat by chemical reaction in the absence of flame to initiate the combustion, or self-ignition is called auto-ignition. This type of self-ignition in the absence of a flame is known as auto-ignition. The temperature at which the self-ignition takes place is known as the self-igniting temperature. The pressure and temperature abruptly increase due to auto-ignition because of sudden release of chemical energy. This auto-ignition leads to abnormal combustion known as detonation or knocking, which is undesirable because of bad effect on the engine performance and life. In addition to this, knocking puts a limit on the compression ratio at which the engine can be operated, which directly affects the engine efficiency and output. Detonation or knocking. Knocking is due to auto-ignition of end portion of the unburned charge in the combustion chamber. As a normal flame proceeds across the chamber, pressure and temperature of the unburned charge increases due to compression by the burned portion of the charge. This unburned compressed charge may auto-ignite under certain temperature conditions and release the energy at very rapid rate compared to the normal combustion process in the cylinder. This rapid release of energy during the auto-ignition causes a high pressure differential in the combustion chamber, and a high pressure wave is released from the auto-ignition region. The motion of high pressure compression wave inside the cylinder causes vibration of engine parts and a pinging noise, and it is known as knocking or detonation. This pressure frequency or vibration frequency in SI engine can be up to 5000 cycles per second. As we discussed, detonation is undesirable as it affects the engine performance and life, as it abruptly increases a sudden large amount of heat energy in the combustion chamber. Now we can see the effect of engine operating variables on the engine knocking or detonation. So when the compression ratio is increasing, pressure and temperature increases, which will reduce the ignition lag as we have seen in the previous slide. So the tendency to knock will increase. And the mass of inducted charge when is increasing, the heat released and thereby the temperature again increases. So the tendency to knock will also increase. The inlet temperature and pressure when it is increasing, it will also reduce the ignition lag, so the knocking tendency is more. The temperature of the cylinder valve also increases the tendency to knock. When the turbulence is more, it increases the flame speed, thereby reducing the time for auto ignition. So the tendency of knocking will be less. And also engine speed, when it increases, the turbulence increases, so the tendency to knock will decrease. And when the engine size increases, the flame travel increases and it increases the time for auto ignition. So the tendency to knock will increase. And the fuel air ratio, when we use a rich mixture, the tendency to knock will be more. And when the octane number is more or the octane rating is more, we know that the tendency to knock will be less. That's how we call the octane rating is based on the knocking tendency. So when the octane rating is more, the tendency to knock will be less. And if we keep the spark plug centrally placed, then it will reduce the flame front travel distance. So that will also decrease the tendency to knock. Pre-ignition. Pre-ignition is the ignition of the homogeneous mixture of the charge as it comes in contact with hot surfaces in the absence of spark. Auto ignition may overheat the spark plug and the exhaust valve, and it remains so hot that its temperature is sufficient to ignite the charge in the next cycle during the compression stroke before the spark occurs, and this causes the pre-ignition of the charge. Pre-ignition is initiated by some overheated projecting part such as the spark plug electrodes, exhaust valve head, metal corners in the combustion chamber, carbon deposits or protruding cylinder head gasket rim, etc. Pre-ignition is also caused by persistent detonating pressure shock waves scoring away the stagnant gases which normally protect the combustion chamber walls. The resulting increased heat flow through the walls raises the surface temperature of any protruding poorly cooled part in the chamber, and this therefore provides the focal point for pre-ignition. Now we'll see different types of combustion chambers for SI engine. The first type is known as T-head type, in which the distance across the combustion chamber is long, which increases the knocking tendency. Valves are placed at two ends, which requires two camshafts. The second one is called as L-head type. Two valves are provided on the same side of the cylinder and one camshaft is required. And the lubrication is easy for this type of cylinder head. And flow faces two right angle turns to enter the combustion chamber, which will reduce the turbulence. The third one is also a L-head type, which is known as a Ricardo's turbulent head. The main body is concentrated over the valves, which results in additional turbulence during compression. And end gas is very thin layer, which easily cooled and which prevents knocking. The fourth one is called I-head type, which is also called as overhead valve combustion chamber. Both valves are located on the cylinder head. Low surface to volume ratio is there and less flame travel length. The last one is known as F-head type. It is a compromise between L-head and I-head. One valve is in the cylinder head and the other is in the cylinder block. It requires two camshafts. Now we will see the combustion process in a compression ignition engine. In a CI engine, the combustion process is divided into four stages. The first one is known as ignition delay period. The second one is rapid or uncontrolled or pre-mixed combustion phase. The third one is controlled or diffusion combustion phase. And the last one is known as afterburning or late combustion phase. The first stage is ignition delay period. There is a definite period of inactivity between the point when fuel is injected to the point when it actually burns is called the delay period. Okay, it represents the period from the point of injection of fuel to the point when the combustion line separates from the motoring curve. The motoring curve represents the motoring of the engine. That means running the engine without ignition using an electric motor. The delay period consists of physical delay as well as chemical delay. The time from fuel is injected to the time when chemical reaction conditions are attained is called physical delay, in which we have the fuel is getting atomized, vaporized, mixed with air and raised to the self-ignition temperature. Chemical delay is the time of attainment of reaction condition to the time of ignition. The second stage is rapid or uncontrolled or pre-mixed combustion phase. It is also called as uncontrolled combustion. This is the period of rapid rise in pressure. The point from beginning of the combustion to the point of maximum pressure is known as the rapid combustion phase. Heat released is maximum during this period. Longer the delay period, larger will be the pressure rise due to the fuel accumulated during this period. The third stage is called controlled or diffusion combustion phase. Due to the high pressure and temperature from the second stage, fuel droplets sprayed at this time burns faster with reduced ignition delay. The period of controlled combustion is assumed to end at a point of maximum temperature. The termination of fuel injection controls this stage. The last stage is afterburning or late combustion phase. The combustion that continues after termination of fuel injection. The combustion of unburned and partially burned fuel will undergo combustion during this period. The afterburning depends on diffusion and turbulence of burned and unburned fuel with air. The afterburning lasts from a point of maximum temperature to certain duration into expansion stroke. It's around 70 to 80 degree after top dead center. Now we'll see the effect of engine operating variables on the delay period. So when the compression ratio increases, the temperature will usually increase, which will reduce the delay period. And when the engine speed is increasing, the loss of heat to the cylinder walls decreases, which will again increase the high temperature inside the combustion chamber, so that will reduce the delay period. Now atomization, the droplets will be more fine, which increases the surface to volume ratio, that also will decrease the delay period. When output, okay, the fuel air ratio increases, the temperature increases, that will decrease the delay period. Then injection timing, when in the case of early injection, the temperature will be less since the compression is yet to complete, so the delay period will increase. When the quality of the fuel is more, that means when the cetane number is more, we know that the cetane number is corresponding to the knocking tendency of the fuel, and when the delay period is more, knocking tendency will be more in the case of a compression ignition engine. So when the cetane number is more, the delay period will be less, and when the intake temperature is more, the delay period will be less, and when the intake pressure is more, the delay period will be less. Diesel knock. In CA engine, detonation occurs in the beginning of the combustion process. In CA engine, the fuel and air are imperfectly mixed, and hence the rate of pressure rise causes an audible knock. High engine vibration is a symptom of knocking. There is no pre-ignition or premature ignition as like in SI engine. Now we'll see different types of combustion chambers for compression ignition engine. The most important function of a CA engine combustion chamber is to provide an air swirl. Air swirl is an organized movement of air in combustion chamber to produce high relative velocity between fuel droplets and air. The onset of combustion will cause additional turbulence if the proper shape is to given to the combustion chamber. This is classified into two, direct injection or open type combustion chamber and indirect injection or divided type combustion chamber. In the case of a direct injection type combustion chamber, the combustion space is essentially a single cavity and pressure remains same throughout the combustion process. The advantages are low surface to volume ratio, hence low temperature loss, and no cold starting problems, and multiple nozzles can ensure fine atomization. The disadvantages are high fuel injection pressure is required, then direction of spraying is very critical. Now we'll see different types of direct injection type combustion chamber. The first one is shallow depth chamber, in which the depth of cavity is small. It is used in large engines. Cavity diameter is large and squish is low. Squish is low means the turbulence will be less. The second one is hemispherical chamber, in which squish is again low. The depth diameter ratio can be varied to get the desired turbulence level. The third one is a cylindrical chamber. The shape is a truncated cone with base angle 30 degree. Squish can be varied by varying depth, and masked inlet valve is used for improving turbulence. The fourth one is toroidal chamber, which provides powerful squish and good turbulence. Spray cone angle is 150 degree to 160 degree. Now we will see indirect injection type combustion chambers. The combustion space is divided into two or more compartments connected by a restricted passage. This creates pressure differences between them during the combustion process. The advantages are injection pressure is low, then direction of spray is not important. The disadvantages are poor cold starting, and SFC is high due to loss of pressure due to air motion. Loss of heat is high due to large transfer area. Now we will see different types of indirect injection type combustion chambers. The first one is a swirl chamber. It consists of a spherical shaped separate chamber. It is located in the cylinder head. 50% of air is transferred to here during compression stroke. The throat is aligned tangential to the combustion chamber. The tangential direction flow gives strong rotary movement. After combustion process, the combustion products rush back to the combustion chamber. This type of combustion chambers are used in adverse conditions where fuel quality is poor and economy is not important. The second type is called a pre-combustion chamber. It consists of a separate chamber connected with the combustion chamber through a number of small holes. The pre-chamber will have 10% volume of combustion chamber. The compression forces some air into the pre-chamber where fuel is injected and combustion starts. The pressure rise inside causes flaming droplets and combustion products to rush into the combustion chamber at very high velocity. This will create strong secondary turbulence and the distribution of flaming fuel throughout the combustion chamber. 80% of the combustion occurs in this combustion chamber. Pressure rise is low compared to an open type combustion chamber. The last type is called air cell chamber, in which the combustion chamber is divided into two parts, the main combustion chamber and the energy cell. The energy cell is divided into major chamber and minor chamber, and they are connected by a narrow passage. The energy cell is connected by a narrow passage with the main combustion chamber also. The fuel is injected inside the main combustion chamber. Due to the restriction, pressure is less inside the energy cell and hence high pressure fuel partially enters into it. The combustion occurs inside due to swirl and then it gets pushed into the main combustion chamber. Now we will compare the knocking of SI and CI engine. In SI engines, detonation is caused by the autoignition of the end gas towards the end of combustion, whereas knocking in CI engines is due to autoignition of the first charge at the start of combustion. Therefore, to avoid detonation in SI engines, autoignition of the end gas has to be prevented, and in CI engines, earlier possible autoignition should occur. The air-fuel mixture that self-ignites in SI engines is homogeneous. Due to this, the rate of pressure rise and hence the intensity of the detonation is substantial compared to CI engines, whereas there is no homogeneous air-fuel mixture present at the time of self-ignition in CI engines. The compression ratio has to be limited in SI engines beyond which the detonation would occur. But in CI engines, higher the compression ratio, lesser is the ignition delay and lesser probability of detonation. Now another difference is larger size of cylinder promotes detonation in SI engines, whereas detonation in CI engines is reduced with the same. For these reasons, engines with a cylinder diameter larger than 250 mm are almost always of compression ignition type. Now the fuels found good to prevent detonation in SI engines have longer ignition delay time, which proves to be poor for preventing detonation in compression ignition engines. This means fuels having a higher octane rating have poor cetane rating and vice versa. With this, we come to the end of this lecture series. Thank you and wish you all the success.